Welcome everybody to the CrySP speaker series on privacy. It's our great pleasure to have, unfortunately in this remote setting, we would have loved to have had him in person, of course, but we have David Evans from the University of Virginia. David is an expert in security and privacy and in, oh look who wants to help introduce David. This is Luna. Luna. The best thing about the pandemic, I think, is that all work meetings have been substantially improved with the presence of cats. As I was saying, so David is an expert in security and privacy, in secure multi-party computation, where he has a book. He has another book I recently learned, a children's book about oh, is he going to go get it? There you go. A children's book about computability, which is awesome. Another awesome thing about David is he was the person who invented the systematization of knowledge papers at Oakland, which have been a great success and have now been adopted by many of the major conferences in security and in other fields as well. So that's been a great impact on the research community. So David's going to talk to us today about when models learn too much. So take it away, David.
So thank you both to Luna and Ian for the very kind introduction, especially plugging my children's book, which I always appreciate. Before I get into the talk, and Ian doesn't know this, but I wanted to mention that the very first security paper I read, at least the first one I ever remember reading, was actually his paper with the great subtitle on confining the wily hacker. This is a paper that was in 1996 in Usenix Security, and this was a paper that really got me into security research. Some of it may seem a little dated to read now because it talks about popular programs such as Netscape at the beginning of the abstract. Old timers remember that well. But the main ideas in it are still highly relevant, and one of the great things about the paper, the main themes in the paper are in a nice box with all capital letters. So it's not hard to find them. This is not directly connected to what I will talk about today, but I think it's still something that's really important to think about in security, that you can't do harm if you don't have access. So what I'm gonna talk about today is give a general introduction to the area of privacy and machine learning, and talk about some of the work that my research group does in this area. The main theme for my research group now is to try to close gaps between theory and practice, especially focused on security and privacy of machine learning these days. And there are huge gaps there for both security and privacy. We have some really cool, strong theoretical results that say things are impossible or that say things are possible, often contradicting each other. And then we have empirical results that in security definitely tell us everything's broken all the time, which is often the case. In privacy, we actually have some fairly practical results that say many things, despite everything being broken all the time, many things that we actually do seem to kind of work. So there are big gaps between what the theory tells us and what we actually understand about what happens when systems are built and deployed in practice. The main focus that I'll talk about today is closing gaps between theory and practice in privacy preserving machine learning. Most of the work I'm going to talk about was done by my PhD student, Bhargav Jayaraman, working with an undergraduate researcher in my group, Katie Nippmeyer. Some of the work I'll talk about is on property inference, which Anshuman Suri is leading. And we collaborate with researchers at UCLA. Changjang Gu is a professor there, and Ling Xiaowan is finishing his PhD. So there are two big privacy issues in machine learning. And these are often confused. They're not given clear names. I'm going to try to give them clear names today, which I hope others also use. But there aren't really well-established names for these. But the distinction is between data privacy and inference privacy. And data privacy is about, you've got some data, it's sensitive, you want to protect it from exposure while you do computation on it. That's a fairly well understood area. We have lots of good theory, we have semantic security, we have methods for proving that systems, at least designs satisfy those definitions. And we have fairly mature practical technologies like multi-party computation, secure enclaves in hardware. And the gap between theory and practice in this space, I think, is actually quite small. What's missing is the right trade-offs between cost and privacy. But in terms of understanding what we can get when we build systems from the theory, that gap is fairly small. On the other hand, for inference privacy, our goal is now we're going to do some computation. We're going to assume that we own the data. We're not worried about exposing it during that process. But at some point, we're going to release an output. Most computation to be useful has to release an output. And the concern is, what is it that an adversary who has access to that input, an adversary who has access to that output can infer about the inputs to the computation. So this is an area that is much less well understood. There's one big theoretical tool that has emerged over the past 15 years, which is differential privacy. So there's some really nice mathematical results, some great theoretical definitions, and there are tools, a large set of tools that can achieve differential privacy. There's some actual deployments and some very huge high-profile ones, which I'll talk a little bit about soon. But there's a huge gap between theory and practice. Right? What the theory gives us is very strong guarantees that are usually meaningless in terms of the domains that we want to use them for. And what the practice gives us is, it seems like for many scenarios at least, there is a way to actually produce useful outputs without totally compromising privacy. But lots of questions about what that is and understanding those trade-offs. So before I get into the new work, I want to give a little bit of a tutorial on differential privacy. I apologize that I know many of the people in the audience are already experts on it, so hopefully you'll tolerate this, but it's a very important notion that's often misunderstood. Definitely, if you want to get into more depth on this, I would encourage watching Gautam Kamath's videos. He's got a lecture series on differential privacy. But the notion of differential privacy is actually a relatively new one. This is already 10 years after Ian Gilbert's paper that I mentioned in the introduction. Inference privacy goes back much further. There was work on inference privacy, mostly in the database community, going back at least to the 60s, and many attempts to come up with formal notions of privacy. But they were all kind of broken. And the main thing that was broken about all of them, they were both broken in practice. People would show, yes, here's something we can learn that you didn't expect would be possible to learn against the system. But the main reason they were broken was they didn't account for auxiliary information in any principled way. They couldn't account for, well, if the adversary knows something outside the system, how they might use it. And that was the key insight in differential privacy, was that you could bound the inference probability ratios in a way that didn't depend on any constraints on the auxiliary information. So here's what the definition is. It's that we have a randomized mechanism. So definitely we need some randomness. And it satisfies epsilon differential privacy if for any neighboring data sets, the probability that you know something based on the output that you didn't know that can distinguish those two data sets is bounded by e to the epsilon. And this is a very general definition. Right? You can decide what neighboring means. You can decide if this is adding one entry or changing one entry in the data set, but it could mean something else. And it doesn't have any constraints on what else the adversary might know. It bounds what they learn in addition to what they already know from the output of the computation. And it gives us a very strong mathematical guarantee. Computer scientists always like to talk about asymptotics and not focus on actual numbers, but the actual numbers here matter a lot. So the inference bound is only meaningful when the privacy loss budget is low. It still gives you a nice formal guarantee when the privacy loss budget is high, but it's bounding the inference ratio in the thousands or millions or something well beyond where it adds any meaningful uncertainty to what the adversary will learn. Okay, so the way to satisfy differential privacy, right? Differential privacy itself is just a definition. Often the term is misused to mean a particular mechanism or assume something about the mechanism. It's a definition. It does suggest the kind of mechanisms that could be used to achieve it. And the most common way to achieve it is to add noise to the output of computation. To satisfy a given privacy loss budget, we need to figure out the right amount of noise to add. And that depends on the sensitivity of the output to the input. How much can the output change based on the input changing by 1 delta in terms of what a neighboring data set is. So that's what you need to do to satisfy it. And this has been a tremendous, both critical in the academic community and a box office triumph. Differential privacy has been announced at keynotes at Apple's Worldwide Developer Conference. This is from 2016. And it's in use lots of places, not just at Apple, but at Uber. Probably the most important and careful deployment is the US Census, which was done in 2020. Results have not been released yet. There's lots of issues, but everyone loves differential privacy. It's really taken over the academic community, and it's having great deployment in industry. I should take that back. Not everyone loves it. Alabama thinks it is causing them great harm. So there's a lawsuit that Alabama is bringing against the Department of Commerce for running the census for using differential privacy or planning to use differential privacy on the result. And there are lots of misunderstandings and political motivations behind this lawsuit that I definitely don't want to get into, but it does get this fundamental trade-off inherent in any privacy mechanism. And that trade-off is, if you're providing privacy, you're making the results intentionally a little bit incorrect. Right? And this is something that, at least when a court looks at it, or in Alabama, politicians look at it, sounds pretty concerning. Right? You're intentionally making the results incorrect. And this is the fundamental requirement to have privacy. There's always a trade-off between privacy and utility. If you have any if some sensitive data has any influence at all on the result of a computation, there must be some privacy loss. There's no way to claim there's no privacy loss without also preventing the data from having any influence at all. What differential privacy formalizes so well is this trade-off, that we know with this privacy loss budget epsilon, we have a parameter we can use to trade off more privacy and utility. As we increase the privacy loss budget, we get more utility and we have less privacy. Eventually, we could think of it going to infinity, we would need no noise at all, and we would have no loss in utility. But what matters is how you decide that privacy budget. And if you look at what Apple's doing now, which is much better than what they were doing originally, they do have documentation that says, it's not just we're getting the marketing value of using differential privacy, we're actually committing to a specific privacy loss budget. And they're committing to privacy loss budgets of things like 8. But 8 that keeps resetting every once in a while, and it's 8 sort of per user, but per device. And so 8 is off the chart that I have here in terms of whether that gives you a bound on inference. And there's no real notion of where these numbers came from or why. If you read the Alabama census lawsuit, you can see that they're talking about the actual privacy loss budget the census will use for the 2020 census has not been determined yet, but the ones that they talk about using are around 0.2, so very low privacy loss budgets, which means adding relatively high amount of noise, but when you've got a larger amount of data, that noise will be less harmful to the results, but with a concern about meaningful privacy. But the important point they make, which is quoting the Census Bureau and many others have made, is that deciding the privacy budget is not a technical question. Right? This is a policy question. It's a decision about how much accuracy are we willing to give up, how much utility do we give up for privacy, and what's the maximum amount of privacy risk we're willing to tolerate. Okay, so how does this apply to machine learning? Well, machine learning, the output of a computation is a model. The input is a training data set. So if we want to have a model that we know we can limit the amount of inference that can be done on the training data from the model, we need to add noise somewhere in that process. And the most straightforward place to add it is the output. Right? If we can perturb the model itself, adding noise to the adding noise to the parameters of the model, that will limit the inference. And for convex machine learning, we know how to do this pretty well. There have been a number of results going back to just a few years after the original differential privacy notion was invented that have shown we can do convex learning tasks. For simple tasks, all of these are binary classifiers using output perturbation. And with a fairly low privacy budgets, all these are less than 1. The challenge is if we want to do complex learning like deep learning, where most of the hype is these days at least, but any kind of non-convex learning, we don't know how to compute the sensitivity of the whole learning process. We have a challenge of knowing how does the output of the learning depend on the input training data. And since we don't know how to compute the sensitivity for those complex learning processes, well, we need to do something else. We need to add noise during the learning process. And this is what's called gradient perturbation, where you add noise every time you calculate gradients. Those are calculated on the sensitive training data. You add noise there to satisfy your privacy loss budget. And then you release the model. So what this means is you need a huge amount of noise. So the first attempt to provide differential privacy for deep learning was about 5 years ago. This gives you this solid, nice formal privacy guarantee that differential privacy does, that bounds the inference risk of any element being included in that data set, but needed a privacy budget of 369,000 something. So this is such a high privacy loss budget that if you're talking about the uncertainty an adversary has when they try to do inference based on the model, they have more uncertainty from the cosmic ray probability of hitting their processor and change the result in the computation than they do from the noise that was added to achieve this formal guarantee of differential privacy. So this wasn't really going to be valuable in practice. What people came up with subsequently was the way to potentially get learning with privacy for these complex learning is to relax the definition of differential privacy. And what was done is instead of pure epsilon differential privacy, where you have this strong guarantee of an inference round, you add a failure probability. That's what the delta is here. They're saying that with 1 minus delta probability, the inference bound ratio is satisfied. But some of the time it might fail. And at least in theory, that failure could be catastrophic. In that delta fraction of instances, all the information about that input might be revealed. But in practice, the mechanisms that we use don't actually lead to catastrophic failures. But they do, they aren't enough to satisfy the standard differential privacy definition. And what this relaxed definition allows us to do is improve the composition. So the big problem with gradient perturbation, every time we update the model, every time we compute the gradients using the training data, there needs to be privacy noise. And that accumulates. You have this nice composition theorem for differential privacy, but it accumulates linearly. So if we did t iterations, we would end up having t times epsilon differential privacy, where epsilon is the privacy loss budget used for each iteration. What the relaxations allow is a way to make that analysis tighter and get to, instead of scaling with t, scaling with square root of t. And there have been a number of different ones. The one that seems to be the best currently is Gaussian differential privacy. But all of these are finding ways to tighten the analysis based on allowing the small failure probability. And this has resulted in success being able to do deep learning with differential privacy, with privacy loss budgets that are kind of in a fairly reasonable range, but still in a range where there is a high, the actual inference guarantee is not very meaningful. And if you actually try to test and understand this privacy utility trade-off, you end up seeing something like this. And these are results updated from what was in our paper in using security a few years ago, that as you, for low privacy budgets, so the accuracy loss of close to 1 means you've lost everything. The model hasn't learned at all. As you increase the privacy budget, you end up with lower accuracy loss, but in these results, even up to epsilon of 100, you're still losing a lot of accuracy. And if you were thinking about what would be acceptable for a model to be deployed, probably you would be somewhere thinking, well, the privacy loss, if it is sensitive data, we want an epsilon not much bigger than 1. Already that's increasing the inference risk. But really for most deployments industry would care about, and most places people want to use models, we don't accept any accuracy loss. The accuracy loss has to be really low. So we are a long way from this region, which is probably the region where things could actually be acceptable. Okay, so this looks like there's a long way to go and no useful trade-offs now between privacy and utility, at least for the kinds of non-convex complex learning that we want to do. But it doesn't answer the question of what is the real leakage risk. The differential privacy guarantees are really strong. They cover all possible data sets. They cover all possible adversaries that might have auxiliary information. But for at least these tests, the actual concrete values we can get for epsilon make the guarantee meaningless. On the other hand, we have some attacks that we know about. We can try to simulate actual attacks. We can see what we can actually learn. And when we simulate attacks, when we try to actually do inference attacks on models, they have very limited success. And the more we try to make the scenario realistic, the less success they have. Of course, the attacks only get better. Right? The fact that the attack succeeds at all should worry us as security people. So we need to better understand what the limitations of the attacks are and what are things that we could do maybe to strengthen the guarantees and close this gap between what we can see from attacks and what we can guarantee. Okay, I mentioned if anyone has any questions, definitely to feel free to ask. I think I can see them in text, or if you raise hand, I think Ian can promote you to ask a question. But this is your chance if you have any questions about the setup or the definitions that I've talked about to ask. Okay, so I'm going to talk about different kinds of inference risks that might happen when a model is published. And the key distinction that I'm going to make and that we'll see as we talk about these is between what you can learn about the data set itself and what you can learn about the distribution. And those, in some sense, are, it's a subtle difference, but I think it actually makes it very helpful to try to understand how these attacks are different and what think about the space of attacks. The first one that I'm going to talk about is membership inference. And membership inference is showing if you can answer the simple question. You've got a model trained on some data set, and what the adversary wants to do, they have one record that might or might not have been used in the training data, and they want to learn whether or not it was. This is in some sense, the sort of attack that links best with differential privacy. This is almost exactly the definition of differential privacy to know, can you tell the difference between two neighboring data sets? In this case, it's one that contains X and one that does not, that were used to train the model. It could be a serious privacy threat. So it could be the model was trained on patients with some medical condition, and you want to know if someone is in the model, that means that they had that condition, which you otherwise don't know, but you do know enough about them to generate that record X to test. But the main reason membership inference is at least a focus of a lot of the research in this area is it's really a simple attack to define and measure and to try to understand as much as we can about what's leaking. So this was formalized by a paper in CSF a couple of years ago that formalized it as a cryptographic game. And the idea is that the adversary is trying to guess this randomly sampled selection bit. And the bit tells you whether the record that is given to the adversary was either from the training data set or just from the distribution. And if you can distinguish records that were in the training data set from ones that were not in the training data set, that shows that you're able to do membership inference. So a generic membership inference attack assumes that you've got some distribution, universe of data. The model developer has some subset of that as the training set. The adversary has some candidate pool, has some records. It could just be one, but it makes more sense if they have a pool of records and they're trying to determine from that pool which ones were members of the training data. And the adversary is going to build some prediction algorithm, try to make a prediction for each candidate whether or not they're a member. The early prediction algorithms were meta-classifiers. So a meta-classifier basically means you train a bunch of classifiers, you train some on one data set, some on another, and you see if you can distinguish them. The nice thing about meta-classifiers, and we'll use these also in the property inference that I'll talk about later, is you don't have to understand your problem at all to use them. You just need a lot of compute cycles, you need to train a lot of models, and they, if they make good predictions for you, you have a result. That's also kind of the downside of meta-classifiers. Even if they work, you don't understand your problem. So what was discovered shortly after this in the Yum paper was you can do as well in most cases by doing something much simpler, where you don't need to train meta-classifiers. All you have to do is test the model on the input and look at the per instance loss. So how does the model's prediction on the input differ from its label, what the correct prediction would be. And the intuition behind this is that the per instance loss will be low for training members, will be lower for training members than it would be for non-training members. And this is because the model has overfit to the training data. So in order to evaluate how effective these attacks are, we need to think about what the attacker's goal and try to have a metric that captures it. One of the common metrics that is used in this area is membership advantage, which is just the difference between the true positive rate and the false positive rate for the membership predictions. If this is positive, this is a sign that the model is definitely leaking something. You're doing better than random guessing. But it doesn't really tell us whether the adversary could do something useful with that leakage. It just tells us that there's something leaking. Because the goal of the attacker is probably something like determining for some of the instances in this candidate pool, are there any that are more likely enough to be members to do something actionable? So what we would advocate for looking at instead is the PPV, the positive predictive value, which is a measure of if you get a positive out of your prediction algorithm, how likely is that to mean that it's actually a true positive? So this is more meaningful to most attacks. And so to make the attack work, you've got to select a threshold that you use as your decision point where you say, this is a member, this is not a member. One thing I'll mention now, like one of the reasons that PPV is a useful metric is as we change the prior, this is going to give us an understanding that these attacks depend a lot on having a candidate pool where the prior is high. So it's much harder for the attack to succeed if there are few members in the candidate pool. And I won't get into that more in this talk, but definitely the paper looks at this issue some, and there's things that make it much harder for attacks in the settings that are probably more realistic, where most of the candidates are not members. Since if most of the candidates are members or they're equally members or not, it might not be such a harm to be identified as a member. But what the attacker needs to do now is they're going to run this attack. The prediction algorithm is going to give them some value. If they're using the Yum attack, they're getting the per instance loss of all the instances. And they need to decide where to set the threshold to say this is a member and this is not a member. And one thing you can see from this graph, there is a difference. So this intuition that the members should have a lower per instance loss than the non-members is definitely supported by this result. But they overlap, right? There's not any threshold you could pick that would give you only members or only non-members. At least I should say only members. There's no threshold that you can pick to say confidently that this is always a member. So what the threshold selection algorithm does is find a setting for that threshold that maximizes some adversary goal. And it could be maximize the true positive rate given some tolerable false positive rate. It could be to maximize the PPV or some other goal. If you look at the impact of privacy noise, so the graph on the left, this is the same as what we saw on the last slide of a model trained without privacy noise. Once we add privacy, and this is still with a very high privacy loss budget, so not adding too much noise, it flattens out that curve nearly completely. One thing to see, like just a very high privacy loss budget is adding very little noise has a big impact on the attack. But it is asymmetric, right? guarantee that differential privacy gives us is protecting the neighboring data sets. It's not making any guarantee about the non-members. So if we were worried about exposing non-members as non-members with confidence, the privacy noise is actually increasing the adversary's ability to do that. And for the really, really low threshold false positive rate, the privacy noise actually helps. There's a small number, like the lowest false positive rate you could get without the privacy noise was 10%. The lowest false positive rate you can get with it is 1.2%. So that even though it's providing the differential privacy guarantee, it is actually helping the attacker with certain goals, but not enough to be a successful attack. So here you can see what those trade-offs are more clearly. And this is the model with no privacy noise. As we adjust the decision threshold, we can find a point that maximizes the PPV. But you'll see it never gets that high. It never gets above 80%. Right? So for an adversary that would cause harm to someone based on identifying them in the data set, there's still a lot of plausible deniability here. So probably not something that would, having the model would change what the adversary would do. So if we are concerned about adversaries that would get actionable information, they need to find high PPV for some inputs. So we need a better attack. And the attack that my student Bhargav came up with is based on a very simple idea that has, starting from the intuition of the YOM attack, that if the model overfits, the training examples will be at minima in the loss curve, but saying that, well, it doesn't need to be a global minimum. What's likely is that they're at a local minimum. So if we start with a member record, if it is a training record, it's likely if we sample the space around that record, the per instance loss will go up. If it's a member, if it's not a member, it's as likely to go up as it is to go down. And so we can sample that and see how often, as we sample noise around the training, around the record, the actual per instance loss goes up or down on those new samples. And what we find is that that property does hold. That the blue line is the members, it's shifted to the left of the non-members line, which means the loss is increasing more of the time for the members. And we can find a threshold where this curve looks pretty similar to the curve that we saw for the previous attack, except at the far left of the line, where we can see if we move this threshold far to the left, we can find regions that are almost all members. I will point out, this is again a model with no privacy noise. If we have a little bit of privacy noise, this effect goes away. Now the curves look very similar. Okay, so we can set that threshold, and because this attack now gives us this region where there is a maximum, we can get a very high PPV by setting a very high threshold. It's not going to cover many of the inputs, but it will give us a high PPV for the ones that it does identify as members. So at least for some attacks, this is a much more threatening attack than the attacks that might have a higher advantage, but never are able to identify any inputs as high likelihood members. So if you know your Welsh mythology, if there's a Merlin attack, there has to be a Morgan attack as well. The hard part of coming up with a Morgan attack is you need to find something that matches the backronym correctly, which it turns out we can find, which is this. So that the idea is just to combine the two attacks. So it's going to combine the per instance loss and the Merlin ratio, which is the loss increase. And looking at that as a scatter plot, we can see that there are regions that are very high PPV of being members. And we can learn those thresholds on a separate data set. And end up getting a threshold where the max PPV is very close to 100%, where everything in that region that would be identified as a member with high confidence is actually a member. And you can see that the region actually has both a lower and upper bound of the per instance loss, because the ones that are kind of where the Merlin attack is failing, right? So where we have a high Merlin ratio, but still have non-members are ones where the per instance loss is very low, which kind of makes sense because there's less room for it to change. Where the ones where it's high confidence are the ones where it's clearly a local minimum. Okay, so I'm going to leave membership inference there and move on to talking about property inference. This is a very different kind of attack. Instead of learning about individual records, now we're learning some statistical property that's global about the data set. But let me give you an example of what that might be. So suppose we are training a handwritten digit classifier. MNIST is kind of the most famous problem in machine learning, the most famous data set. Let's suppose that now it's a secret data set, very sensitive handwritten digits, but we're training a model to solve the same problem. And what the property inference might allow is an adversary wants to learn, well, what fraction of the samples in our data set were written by Canadians? And the algorithm might output, well, 15%. So that would be property inference if you could do that. And maybe you can, because maybe Canadians write funny sevens with slashes through them, and others don't. Probably not too harmful. Another example, maybe we're training a network model to distinguish web and DNS traffic. And what the adversary wants to learn was there Tor traffic in that data set? And maybe the algorithm can learn that from the model. So these kinds of attacks have been demonstrated. And there's a handful of quite interesting ones in papers. I'll mention a few of these. The first paper on property inference that introduced it was from Giuseppe Adanesi and his group in 2013, and showed that if you trained a speech recognition model on speakers that spoke with an Indian dialect, still speaking English, it's an English speech model, versus on non-Indian speakers, you could distinguish which one was which. But it's a very extreme difference in the data distribution. Another example, this is from a more recent paper, is if you have this US Census data set, which we'll use for some of the examples later, you could tell the difference between a model trained on majority women and a model trained on minority of data set, data distribution being women. So there are examples where you can do property inference, and there could be scenarios where this is a serious privacy violation. If you can learn that, it's not a violation to individuals, it's a violation about the organization that did the training. So the question is, can we define these formally? Because all of the papers, all the previous results on property inference, they have to make this argument that yes, this is a real issue. This is an attack of some kind, but there's no real clear definition of it. And the definition that we think is the right one, at least the best one we've come up with so far, starts from the notion of membership inference that came from Yum and others in this paper. It says, well, the big difference between membership inference and property inferences is that property inference is on the distribution, not on the data sets. So what we want to do is, instead of distinguishing an input, now we're going to distinguish between two distributions. We're going to assume that there's some filter that changes the distribution to one or the other. Still set it up as a cryptographic game where we sample a bit that selects which distribution we're using, then samples the data set. So the data set is still sampled from that distribution and trains a model, because what we care about is the distribution, not the particular data set. And then the adversary's goal is, can they predict that selection bit? So as a more concrete example that is motivated by the results in those papers, if we look at the data set property bias. So we're going to make our filter that selects the distribution from the original distribution, change the probability distribution, and select records based on the probability of being in the class male. And so we can have one data set where it's balanced. So that probably is going to be 0.5. Another data set where we're going to set alpha as the probability. So data set 0 is 50% male, data set 1 is alpha male. And then we're going to see if we can distinguish between those. And the approach is using metaclassifiers. This is based on the most successful property attacks to date, and shows that yes, there is a way to distinguish them, but around where the probabilities are really close, like remember the original was 0.5, we set it up to be balanced, the accuracy is really low. You're definitely leaking something. It's better than random guessing. You have to get pretty far away to have some accuracy, and it's only at the real extremes that you can have a high confidence prediction of which distribution of the data, the training data was from. The other downside, it's very expensive. These are meta classifiers, so you have to train thousands of models to be able to get these results. So we're just at the beginning of the property inference work. This is definitely not enough to be convinced that it's not a threat, but there are limits definitely on what can be done today, as well as what might be possible in terms of property inference. That's something that I think is interesting to understand. But the main thing that, to me, I think has been valuable looking at the property inference is thinking about inference risk in terms of these two separate things, of distribution inference risk and data set inference risk. And this gets to the last kind of inference risk I'm going to talk about, which is attribute inference as well as imputation, which I think that's the distinction I want to make here. So what attribute inference is now the adversary knows some record, knows non-sensitive attributes of it, but there's some sensitive attribute that the adversary does not know. And in this case, let's say these are records about people. This is like what's in the US Census data set. And what the adversary wants to do is predict the sex of the person. And so they have a record, and the prediction algorithm is going to try to predict it. If they have a model that was trained on that data set, including the record that they're trying to do this prediction on, then it would be considered attribute inference. And the prediction algorithm will output a prediction as the actual value of that attribute. Another kind of inference risk, but this is really not related at all to machine learning or having access to the model, is just data imputation. And data imputation is also something that goes back many decades, where now what the adversary has, they know the distribution. Maybe they have data they can sample from that distribution. Maybe they know something else about it. And they train a prediction algorithm based on the distribution, and based on a record and that algorithm, they can make the prediction. They don't have a model. They don't know anything about it. It doesn't matter whether your data was contributed to train the model or not. So the tricky part is that lots of the work that has produced results that seem like attribute inference, you can't tell if what's going on is really attribute inference, or is it really what the adversary is learning is the data distribution. They're just learning it from the model, right? So maybe what's happening implicitly is the adversary is using the model to learn about the data distribution and then making the prediction. And certainly if the model is a deep learning trained model, you can't tell that that's not what's happening, even though you're not explicitly saying, let's learn about the distribution. Okay, so in order to claim that there's meaningful attribute inference going on, I think we need to distinguish those two things. And so the model that we think is the right one is to say that, yes, the prediction algorithm has access to both the data distribution and the model. And the key question is, do they learn something from the model that they couldn't learn just from the distribution? If it's what you can learn from the distribution is just imputation, it's still maybe a privacy risk. And in some sense, it's a more frightening one, because it says, well, if it's attribute inference, maybe you have a choice whether your data is used to train the model or not. And if it's not, you don't have that risk at all. If it's imputation, you have no control over it. If someone knows enough about you and wants to impute something, if they've got a good imputation model based on the distribution that you're part of, then they'll be able to do it. So the experiments we've done in this, and this is also very, very early work that I'm talking about, use this US Census data set. That's one of the data sets in the UCI repository. And it's got 14 attributes. The task is to predict the income, whether it's below or above $50,000 a year, based on those attributes. And it's got attributes like age, working class, education, marital status. If you're wondering what married AF spouse is, that's married with a spouse in the armed forces. And so the task that we want to do is see, can you predict the sex attribute from the other attributes? So the imputation model is going to be trained on a whole set of data, seeing all the features except, so that's trained on all the features. And then the task is, can you predict the sex attribute for a record seeing all the 14 features except for the sex attribute? And what the model does is very simple. It's going to try the possible values, there are only 2 in this case, and see which one appears to be more likely according to the imputation model. And if you look at these results, you can see that the imputation adversary is definitely able to distinguish these. So the horizontal axis is the prediction probability that the input is male, and the pink line is the male record. So you can see those are definitely different. You can get a PPV of for male predictions of about 80% here. Note that the data set is imbalanced. It's more than 2/3 male in the data set. So predicting getting a high PPV on male is easier than getting a high PPV on female. But this doesn't tell us if the attribute inference is meaningful. Sorry, if there's this is all imputation, right? There's no model here. There's no learning from. There's no risk of being exposed because of being in the data set, because that's what's there. So what we want to understand is, does the model leak something more? And so the strategy for this is to say, well, now we're going to have a separate attribute inference prediction. So this is the imputation side. The attribute inference is going to look for the model leakage. We're going to now get a model that was trained on the data set, including the record that we're trying to infer the sex of. And we're going to use a very similar strategy what was used for the membership inference to try to see which is the more likely. But we're going to combine those two to make the best prediction we can from both the imputation and the model inference. And there's a hyperparameter zeta here that controls the weighting of those two. And so we're going to tune that hyperparameter to try to maximize some goal. And it could be maximizing the PPV for the targeted value of that attribute. So if we do that for male, what we get is this. We see that the actual weighting emphasizes the imputation. That's what maximizes the PPV. And we're getting very little, if anything, from the model. So the results for the imputation, the PPV was 0.809. So it does seem we're getting a little value from the model, but it's also not clear from this if it's actual attribute inference or it's the model has actually learned something about the distribution that the imputation didn't. And when we test it on non-training records, we see that it's actually the latter, that there's not a difference between training records and non-training records here. For female, it turns out that the model reveals more information. The tuned data parameter is higher, but the improvement in PPV is also barely noticeable. So to wrap up, inference privacy is a very open field. Like there's very little that's really well understood in this field. We can't guarantee privacy in theory for meaningful values of privacy loss. But it seems, at least in practice on the kinds of problems we're looking at, inference attacks are quite limited in practice. I want to wrap up by talking about a talk Alex Stamos gave at Usenix Security 2019. It's definitely a very worthwhile talk. I encourage people to watch it. But he made the point that most of the harm that's caused by computers, and we should cite this as the Stamos hierarchy of actual bad stuff that happens to people online to real people. Most of the harm that's caused is not because of the things the research community worries about. It's abuse. It's not about compromising security of systems. It's about people using them as intended. And if you zoom into that triangle, which he did, you get to this top where the top pixel is broken into its 3 color channels, and you have the side channel attacks that the research community is very excited about. So I'm going to try to make a similar hierarchy for privacy. And in privacy, that bottom of the hierarchy is different. And if you look at, I've got to rename it, of course. First, we're looking at, privacy that matters. Privacy and bad stuff are kind of a little harder to say what it means for bad stuff to happen, but privacy that matters to real people. The vast majority of the triangle is about massive data collection and exploitation, right? It's not about any of the things that we talked about today in terms of inference privacy. It's about the data that's collected and how it's exploited intentionally. The parts inside the paragraph, probably the biggest part, and the next part is data breaches, right? This is where this is a data privacy issue where the data is exposed. Once we get into that top triangle, maybe things like inference attacks show up. Hopefully proper inference is maybe a pixel or 2 in there. But none of these are that, if you look at the actual privacy risk that happens today, maybe it's not the things that I talked about. And as academics, that's probably okay, right? We should be working at things at the top of the pyramid. We shouldn't be so focused on immediate problems, because those are the things the industry should already be working on solving without our help. And we should be looking to the future, motivated by intellectual curiosity. Definitely, some of these things I think should have a real world impact, and are. Certainly differential privacy is having a huge real world impact. But the one point I think is important to think about of this, if you look at most of the research that's happening in this top of the pyramid, the money that's supporting it is mostly coming from organizations that depend on the big bottom part of the pyramid to be able to fund the research that's going on. So that should raise some questions about whether it's being distorted by that, and whether we're focusing on the right problems. Okay, so to get back to the research of the talk, definitely, I think there's lots of interesting theoretical results, and they can provide guarantees, but those guarantees are only meaningful not in the assembly products, but in the concrete guarantees they make. And they also tend to depend on assumptions that are hard to get in practice. The empirical kinds of results can only show how broken things are. We can't ever get a guarantee by empirical results. But we should also be careful to realize that, just because there's some measurable leakage doesn't mean the sky is falling. We also have to think about whether it's enough, and the kind of leakage is something that could lead to actionable harm when used by an adversary. So thank you for that. I'll close there. You can find links to papers and code from my website, and I'm happy to take any questions people have.
Thanks, David. You can probably only hear me, but okay. So if anyone has any questions, as David said earlier, you can either raise your hand or put them in the Q&A box. I'll have one to start. So in the can you clarify for me again what the Morgan attack does? It takes the Merlin attack and the Yom attack and looks at what does it do to those two?
Yes. So it's looking at both. So the way to think about it, let me see if I can show the slide, if I can find it easily. They are, so the Yom attack is looking at the per instance loss, right? And saying that loss is lower for members than it is for non-members. The Merlin attack is looking at is the loss for this instance at a local minimum, and looking at, as you sample around it, how likely is the loss to increase versus decrease. So the combination of them is saying that being at a local minimum matters, and the actual per instance loss value, how close it is to a low loss in general, matters. So that's where the surprising until we thought about it result is that it's not the really low ones. Like where the per instance loss helps you is not because of you want the ones where it's really low. It's you want the ones where you're at a local minimum and the per instance loss is not that low. Because if the per instance loss is really low for this test, that means that almost guarantees that it means the Merlin ratio is going to be high, right? Because you're already at a very low loss. It's more likely just from the sort of distribution of the loss values that sampling around it is going to increase that loss. Where the indication that you're actually a member is much stronger if you're sampling around the instance and seeing that everywhere that you sample the loss increases. But the strongest case of that, if you see kind of this box here, right, it's getting right up to the edge where you start to have higher per instance loss that indicates non-membership. It's a little hard to see all the points in the scatter plot because this is sort of a good mix of the orange and purple in this region. These ones are almost all purple, almost all non-members in the per instance loss side. But where you're getting the strongest signal that it's a member is where the per instance loss is relatively high and it's a local minimum. Because I think at least the intuition that I have behind this is to be a local minimum where the per instance loss is high, it has to be much more overfit. It's much more of a sign of overfitting than if it is a local minimum somewhere where the per instance loss is already very low.
Great. So so Morgan outputs instances for which the PPV will be high, but not very many of them.
Right.
Perhaps.
It will identify a small fraction of the inputs where there's high confidence that it's a member.
Great.
And it's quite a small fraction, right? You can see from the visualization, it's the ones in the region of this box.
Right.
And that's a trade-off. You could say, well, so it is setting these thresholds to maximize PPV, right? If you wanted to say, my goal instead is to identify at least 10% of inputs and identify the 10% most likely to be members, then you would have a larger box that would include some, have a slightly lower PPV. Right? But you could make those trade-offs.
Great. All right. Has anyone else had time to think up a question? Just raise your hand and I'll unmute you, or type it in the Q&A box. Oh, I have a question in a side channel. Can the techniques you talked about in the second half of your talk be used to impute something about fairness?
That is a good question. That is something that the property inference techniques that we've looked at, the connection between fairness metrics and property inference, because it does seem like there should be a connection there. The test that we've done so far, we haven't been able to find it. That the signal that you get from the fairness metrics is not enough to learn, and there should be at least fairness is a very complicated question, and no one knows what fairness should mean. But if you're talking about, does the model make, if you're thinking, let's use gender as our example, does the model make better decisions for men than it does for women? You would think that should be related to whether it was trained on a data set that had an imbalance of too many men in the data set. And that's definitely something people have seen in a lot of the fairness work. If you train your model, the most famous case of Amazon training their model to recognize good employees on your current employees, you end up discriminating against women. That's something that, at least for the kinds of differences we've done, and Anshuman, the student who's working on it, has done a few experiments trying to look at if we could get anything from the fairness metrics. And those are definitely tests of the model's predictions on inputs, right? So they're very much a black box use of the model. It seems like there should be something where the things that we've tried so far have not been able to find any useful connection. But I think it's a good idea to keep looking for one.
Okay, we're out of time, so let's thank David again.
All right, thank you.